Okay, so now we described the measurements of the channels. They were still not discovered at this time, right? So let's have a closer. So it took another 20 years or so after the measurements, the first measurements of these channels, before they were really discovered and described in terms of their structure. So this is, again, a Nobel laureate because of his work. He was actually an electrophysiologist. He was so frustrated by the fact that he was measuring all these ion currents without having any clue how these channels look like. And he completely switched his career to become a structural biologist and tried to make crystals of this protein so they could use Röntgen, X-ray, crystallography measurements to discover the crystal structures of these proteins. And then, what is I think is really beautiful, is that actually he found these kind of structures. And the thing is that it's a little bit of a detail, but Hoskin and Huxley, I cannot go into the details why, but they discovered because of their fitting of the currents that they did mathematical fitting, they could very accurately describe with a mathematical model how these channels would behave. And they predicted actually that these channels, the potassium channels, should have 4 voltage sensors that were acting in parallel. And they found, and this is, they found that this was indeed the case. If you look at the potassium channel here, you have this top view, you have these 4 sensors basically. They're carrying charge that is necessary for sensing the charge differences. You can imagine if this is charged, and if there's a depolarization, that this charge will move in the membrane and that will cause a conformational change. The other thing is that very nicely, you have the pore. And so this is actually the pore where the ions conduct, and somehow, if you look a little bit more close, then you see that the main components of such a channel, in this case the voltage sensitive potassium channel, is you have this pore, so ion channels have to be able to flow through the channel. But as we discussed, they have to be selective, so somehow there's a selectivity filter, and this is actually still not understood in all the details, how does it exactly work. But you have this filter here that makes, there's all kinds of atomic forces that play a role, why these filters are selective for potassium and not for sodium, for instance, and vice versa. So it cannot be only size or charge by itself, because sodium and potassium have the same charge, so that cannot be the way by which these channels are selective. Also not size, right? Because I don't know which one of the two is the largest. I think potassium, probably. That's a larger ion. So that means that you can make a channel that is selective based on size for sodium, because you just make it small enough that only sodium can penetrate and not potassium, but not the other way around. That you make a channel based on size that only sodium, potassium can enter, and sodium not, because the sodium is smaller than potassium, so they will then also be able to flow through that pore. So you need some extra filtering mechanisms, forces that are specific for these ions to make it a selective ion channel. So that is this part, and then you have the folded sensors. Where is it? Yeah, this is these charged parts that move when there's a depolarization going on. And that because they're so connected to the pore, that makes the transition from a closed state here to an open state. And these sensors actually can be, those are quite different between the different types of channels. So we have voltage gated channels, but we also have mechanosensors or chemical sensors. And mechanical sensors, for instance, they bind a certain ligand, and that will activate the channel. A big example, of course, a great example, of course, is the receptors, neurotransmitter receptors. The neurotransmitter binds to these channels, and that will make the channel go from a closed to an open state. But you also have the mechanosensors that somehow can detect pressure, and that makes the channels open. So this can differ quite a lot, but this is quite similar and conserved through all these different types of channels based on what ions it will conduct. Okay? Yeah, this is just to show the evolution of these channels. They all come from a common ancestor, and that's why these channels are so alike. And it's just during evolution, small variations on the channels could make just a big diversity in functionality of these channels, which give a rich repertoire of what neurons and excitable cells, because these ion channels not only are present in neurons but also in the heart, for instance, and all kinds of other cells, to generate these currents. Yeah, the very interesting and convenient and cool thing about this is that actually, electrically speaking, you can describe them all with the same Hodgkin-Lipschitz type of formalism. Right? So how they affect the membrane potential is all described by the same biophysics. And that means that the only thing that you need to include in your models, for instance, if you want to make simulations, is how they are open and closed by what stimulus. Is it neurotransmitter concentration, or is it membrane voltage, or is it temperature, right? But then if you have that, if you the opening and the closing of the channels determined based on these external factors, then how it affects the membrane potential can be described with the same formalism. That means that you can build very realistic models of neurons, including neurotransmission, including maybe temperature sensitive effects, all using the same mathematics. And I think there will be a simulation program that you will use, that you can play around yourself with these parameters, how certain channel parameters affect the membrane potential. Okay? Okay, just quickly go through some of the types of channels. So we discussed already the voltage-gated channels. Here you have different types of channels: sodium channels, calcium channels, potassium channels, chloride channels. You see that they quite, especially from the top, they have the same kind of structure. Then there's the light-gated ion channels that I also briefly already touched upon. So these are, again, similar structures for the core part and the conductivity. This part is different because this is where the receptor part is where they bind the ligands. In this case, is a glutamate receptor, so they bind glutamate somewhere here in this product. You have also acid-sensing ion channels. But you also have, for internal signaling, for instance, a very important one is the calcium-activated potassium channel. So there's a potassium channel that senses the internal calcium concentration. So calcium concentration increases, it starts to become more conductive. This is, for instance, a very important channel that regulates the activity of neurons, or certain types of neurons, right? So during activity, you can imagine that the calcium that flows in increases, because calcium channels are also, you have also voltage-gated calcium channels in the membrane. So every time an exponential arrives, these channels will open, calcium will flow in. So you will get a buildup of calcium in the cell. And at some time that will start to activate these potassium channels to reduce the activity, that this neuron is not firing like crazy, but there's some limit to it. And with all these components you can get very rich repertoire of firing properties of these cells. Then there's other channels like we discussed in the beginning of the first lecture, where you have these different types of receptor signals. Important channels that play a role there for the receptor currents are, for instance, thermosensitive and mechanosensitive channels. This is an example of the thermosensitive channel. Again, from the top, it looks quite similar to what we are used to, but now you have actually two mechanisms for this particular channel, the TRPV1 thermosensitive channels that can sense temperature. So by some temperature-dependent displacement of membrane lipids. Here you have the membrane lipids. If temperature increases, this lipid flips out, and you get that will cause a conformational change of the channel. But interestingly, it also can bind to caspicin, which is the component that makes peppers hot. And the more of this in the pepper, the hotter the peppers are. And that's why you have the sensation of hot, why we think if we eat a hot pepper, it also burns, in your mouth. It's the same receptor, so that's quite interesting. Also for cold receptors, that's the same thing, that they respond to low temperatures, they're activated by low temperatures, but also by, for instance, the compound that's in mint. Is it mint? Is it, yeah? Okay. But it gives this fresh flavor. That's because it activates the same sensor. Quite interesting, I think. It was also only discovered, I think, 20 years ago or so. And then mechanosensitive channels, same idea. You have this conserved pore, but now you have these blades that stick out, and that can detect mechanical force. You can imagine if you push, or if these blades are dislocated, that will, with the rigid structure, they're bound to the pore, that will also activate the channels to become open in the open state. Okay. So this is again a movie for the PET scan method, how you can do this ion channel reconnaissance. I will skip it for now, but I really recommend to look at it. Are there any questions on this part before we go into the last section? If not, okay. The grand finale, exponential generation and conduction. So the learning objectives are be able to reproduce the 5 phases of the exponential and explain which roles the sodium and potassium ion channels play in each phase. To be able to explain what the refractory period is and the underlying mechanism, and to be able to explain how exponentials are conducted along the axon and the role of myelin and nodes of Ranvier in this process. Okay, so this is a very important slide, because this is also, what you learn always about the sequence of events during an exponential. And now the cool thing is that with all the ingredients that we have, Oskar actually could make actually a mathematical description how all these elements interplay, and how they would lead to this particular shape. So first, let's go to the features of the exponential again. So you have the resting state, that's before the exponential. Then there's the threshold. So during a depolarization, for instance, from our electrode, but in the brain, of course, from synaptic input, synaptic currents, you get this initially passive response, but if it exceeds a certain threshold, then you get this depolarization phase, of the rapid rise phase. And that's this dark blue part here. And then you have the repolarization phase, so it goes back rapidly, and then you have your undershoot, and you go back to the resting state. Okay. What happens with the channels during the cycle? So remember, we can actually explain or understand what's going on if we have some mechanism for the change in permeability of sodium and potassium, right? So the resting membrane potential is dominated by potassium. The permeability of potassium is much higher than for sodium. So why is that? That's because some of the potassium channels are open, while the sodium channels are still closed. Okay, as you can see here. So this is, in a very schematic way, the two processes that is in the sodium channel present. So this is the activation and the inactivation. Yeah? Activation is closed, inactivation is open. So here also the potassium channels, the voltage-gated potassium channels are closed, but there are some channels here that are not depicted here, potassium channels that are called leak channels, that are voltage insensitive, that are open. But they make that the permeability of potassium is much higher than sodium because all the sodium channels are closed, and that you are close to the reversal potential of potassium resting state. Okay. Then, if you reach the threshold, that means that you start to activate the sodium channel. So remember with the voltage clamp experiments that Hoskins did, that we discussed, and that if you start to depolarize the cell, you start to activate sodium channels. And now when you activate sodium channels, what happens? Because of the concentration of sodium is much higher outside than inside, you will start to have this flow of the diffusion force is flowing these sodium ions with a high speed into the cell. So positive charges go into the cell that will depolarize the membrane. Okay? But we also know that if we depolarize the membrane, sodium channels become even more activated. Yeah? So this is the positive feedback loop that we start to generate. So this sodium channels open, thereby depolarizing the membrane, thereby activating even more sodium channels. So this rapidly accelerates. That's a brilliant mechanism why this is so fast. Okay? So now two questions. Because if this is the case, why doesn't it go on forever and goes into infinity? Anyone? So it's a positive feedback loop. So in principle, you get more depolarization, more activation, more depolarization, and so on and so on. But it stops here. There's two reasons. Yes? That is a good point, but that's not what happens. And the point is that you need this concentration difference is so high, as we discussed. You only need a few, I think it was 1/1,000,000th, let's say, of the charges that are producing this concentration difference to move from outside to inside to get this huge change in membrane potential. So that's not the case. Yes? Yes, exactly. That's a very important point. So that's where the inactivation comes in, indeed. That initially you have this positive feedback loop because the channels are open, but then also this slow inactivation, which is also depolarization dependent, starts to kick in and slowly starts to close the channels. That's one reason. There's another reason. That has to do with this graph here. Yes? Yeah, that's also something that kicks in. So actually there are multiple processes together. Yeah, so maybe there's actually a third mechanism. So at some point also the potassium starts to increase, starts to be activated, and that starts to hyperpolarize the membrane again. That's true. Remember, it's maybe good to mention that the kinetics of these potassium channels, so the way they're activated, that what you saw in the first voltage clamp experiments is slower, right? So you have this initial sodium current, and then you have this delayed, they call it delayed outward current, and that's because of it's just slower. And that's for a reason, right? Again, if the sodium and the potassium would be equally fast, then during depolarization you would have counteracting forces. So the sodium would depolarize the membrane, but the potassium would hyperpolarize, and there would be no net effect. So therefore it's important that the hyperpolarization effect of the potassium channels is delayed with respect to the activity of the sodium channels, because you need first depolarization before you get the hyperpolarization. But that's indeed also something that specifically is important for this phase and makes that this hyperpolarization phase is much faster than if you would have only sodium channels. But there's one other important aspect why this cannot go on forever, it cannot go off the scale. And that has to do with the reversal potential. Remember that the the closer you get to the equilibrium potential, the smaller the influx will be. Because then, this is the reverse potential for sodium. That means, per definition, that there's an equilibrium between the diffusion force, which makes this sodium going in, and the electrical force which wants to push out the sodium ions again. And there's no net flux, so it never can exceed this sodium reverse potential. Because by that time there's equilibrium and there's no net efflux anymore. Okay, it's a detail, but it's just an important part of the why it cannot go on forever. Okay, so that's the threshold and then the rise phase. So the depolarizing phase is then just the acceleration that we discussed. More channels are opened. I think they start to depict it here by that here you have this channels completely open and here it's start to open again, also start to open, and here all the sodium channels are open. Okay? And then indeed we get the inactivation, so that's when we are at the repolarization phase. So sodium channels close because of the inactivation, and now the slower potassium channels also start to open and they start to hyperpolarize the membrane. So now permeability for potassium becomes higher than for sodium, and that starts to draw the membrane potential back to the reverse potential of potassium. Okay? And now we actually run into the situation that sodium channels are all inactivated, but now all the potassium channels are open. And that means that there's even more potassium channels that are open, so the permeability for potassium is even higher than at the resting state. And that's why we now get really close to the actual reverse potential of potassium. That's what is the undershoot. That's causing the undershoot. Okay? And then it takes time for the potassium channels, because they were now at the hyperpolarized phase, to close again, and then only the leak channels stay open to maintain the resting membrane potential. So this undershoot is because now all potassium channels are open and really pushing it close to the potassium reverse potential. And then go back again. So this is something that you test experimentally with the earthworm practical and also with your simulation practical. Are there any questions about this? So that can mean two things: or you completely are lost, or you fully understand. So I hope it's the latter. Again, if you're completely lost, there is some time. It's just like a primer. If you read again, if you look at the slides, or if you look at the movies, and if you do the practicals, I think things will become much more clear. Two questions. You was first. Yeah.
The reason potassium permeability is lower than sodium is because the depolarization makes potassium channels permeable slower.
Can you say again the reason?
How to put it? The potassium channels become, their permeability rises more slowly.
Yes, yeah, that's the crucial.
That's why there's a period.
Yeah, that's why you first. So the question is, the reason that you have this exponential is that the potassium channels are slower than the sodium channels, indeed. So that's why here the permeability is dominated by sodium channels, because they're open much faster than the potassium channels. And then here they inactivate the sodium channels, and by the time they inactivate, the potassium channels start to open. And this is a slower process. It needs time. If it will be equally fast, it will kill all the activity that you get from the sodium channels immediately, right? It will be counteractive.
Another question.
Yes, another question?
On the protein level, is there any mechanism that we can point out?
That's a good. Well, at the molecular level, what is causing sodium channels to be fast? And it must be, but I don't know. what it is. Yeah. I'm not sure actually if people know the molecular mechanism for this, because I study the proteins that are involved, for instance, in synaptic release. There's also still a lot that we don't know, and it has to do with the fact that actually these crystal structures are very difficult to make, and now we know how they look in a crystal structure, but how they operate during activity, that is something that we cannot measure. So that has all come from simulations, and these are very heavy simulations, so I'm not sure if this is known. I know that for the proteins that I study, a lot of the molecular mechanisms, I think most of the molecular mechanisms are not understood. There was a question over here, yes? The what? The undershoot. It's close to getting to the reverse potential of potassium. It never gets there exactly, no, because there's always other channels that also contribute a little bit. So if you look at this Goldman equation, right, you have all these terms, it's dominated. So that's why this is just writing that it's much larger, but it doesn't mean that this is zero, for instance. Yeah? Say again? If you would have only potassium, for instance, and all the other channels are closed, you end up at the resting member potential, the reverse potential for potassium. What will happen? Nothing. Yeah. More questions? Okay, last 15 minutes. So now the refractory period, I already gave a spoiler basically on what that means. So, but this is just a measurement that shows you that if you give this is again in the exponential of the squid axon, if you apply depolarization, you get this nice exponential. And then if you give subsequent pulses, just a few milliseconds later, then, for instance, here you don't get a full exponential. Here it starts to grow, and it takes a while, about 9 milliseconds for the action potential of the squid, before you get a full exponential again. Okay? And here it's the stimulation interval between these pulses, and the amplitude of the second exponential is drawn here. And you see that indeed only after 8 milliseconds you get around 8 milliseconds you get a full exponential. So this period here in between, basically you don't get full exponentials, and that's called the refractory period. Now the question is, what is causing this? And I think disclosed what the mechanism is. And it has to do with this inactivation of the channel, of the sodium channels. You need to inactivate the sodium channels before they can participate in another round for this exponential, right? And this just takes time. Right after the exponential, all the channels are inactivated. It takes time to recover from this inactivation. That is causing this refractory period. But let it sink in that this simple mechanism that Hoskin actually discovered, they could now not only describe all the features of the exponential in detail, which is a highly nonlinear process. And they actually, again, was too much to discuss in this context, but they have an exact mathematical description, so they really understood what was going on. But on top of that, they were not explicitly trying to describe the refractory period, but as a bonus, and because they understood now the mechanism, they got as a bonus, they got the mechanism also for the refractory period. I think that is very strong. Also that they made the predictions, and of course they couldn't know at the time, but that 50 years later, actually, the prediction about how the properties of the channel was actually confirmed by this molecular structure, but I think is very powerful. The other thing that they didn't explicitly model in their system was an emergent property of the model. So this came for free, let's say, as a bonus from the model, was exponential propagation. Okay, this is again worthwhile to look at it, but we'll not discuss right now. One remark that the inactivation of sodium channels, which is really important, is not shown in this animation. So that's the only critique that I have on this animation. Other than that, I think it's a nice recap of all the things that I explained. Okay. Okay, the last part is the exponential conduction. So what is exponential conduction? The start of the lecture, previous lecture, we said that this was a really important property for signaling in the brain, right? Remember the giraffe with the motor neurons, these signals have to travel more than a meter to get to the muscles, and they cannot lose their strength, they cannot lose their speed, they cannot lose their amplitude. So that requires a mechanism by which this exponential can be generated at the soma and then travels along the axon to the other neurons or to the muscles, for instance. And this is the mechanism by which that is happening, and it requires both active and passive current flow. So remember, the passive current flow is just diffusion of ions, and active current flow is the flow through the ion channels. Okay, when they're activated. Okay, let's imagine that we somehow, by some mechanism, here we do it with an electrode, but it of course could be also synaptic input on the soma. We locally inject current by which we depolarize the membrane. So if we depolarize the membrane, we start this whole cycle of generating the exponential, right? Sodium channels here will be activated, they will depolarize the membrane further, more channels will open, and more sodium ions will flow in. So if you have an axon like this, these sodium channels will start to diffuse, okay? They will start to diffuse in both directions actually. That's depicted with these arrows, it's the diffusion of the sodium. But if it diffuses in this direction, what will happen is that here locally, you will get an increase in the positive charges, so that will effectively depolarize the membrane here locally, right? Because it becomes less negative, so that means, per definition, depolarization. But what happens if you get locally depolarization here? Anyone? Yes? Exactly. So you get all the sodium channels here, these are fresh, de-inactivated channels ready to go. If they feel the depolarization, they also open, and then you get a lot of influx locally here that generates the exponential here. But those ions that flow into through these ion channels will increase the concentration here locally, that will diffuse further along the axon, and then you get a repetition of the process. Okay? So that's how the exponential propagates. Okay. Now, there's a very important thing. This only works if you have propagation one way and not back, right? Because otherwise it becomes a total mess. You get every location, you get new exponentials going this direction, and then here, this direction. They'll be firing all over the place. Why doesn't that happen? Why is it only traveling in one direction, away from the axon, away from the soma? And typically, this exponentials are not generated through pipettes that are pinched into the neurons in your brain. Of course, that's the synaptic input that is integrated through the dendrites that leads to enough depolarization to generate an exponential at the soma. So when it's generated at the soma, it travels along the axon and not back into the dendrites, and also when it's halfway, it doesn't travel back. Yes, why?
I think it was because of the recovery time.
Yes, refractory period, recovery indeed from inactivation again. So this inactivation of sodium channels is very important. Also for this reason is that, like I said, if you have this diffusion of your sodium, that will produce locally a depolarization here. Also, it will produce a depolarization here. But here you have the freshly inactivated, de-inactivated channels. Here the channels are still inactivated. So although you get depolarization here as well, the sodium channels are not activated, so you will not start the generation of an exponential. That's why it only travels in one direction. So, the refractory period is a bonus of the Hodgkin-Huxley model because of the inactivation, but also the propagation in one direction. And the propagation itself, right? That the fact that you could have this active signal traveling along the axon without losing its strength is also can be understood only based on the Hodgkin-Huxley formalism. So by now I hope I made enough advertisement for this model and that you hopefully appreciate how beautiful this work was and how important it was. Okay. Oh yeah, well this is what we just discussed. The question about the X potential, so we can skip that. Yeah. And then there's two final slides. And that's about the speed of doing this. So during evolution, so you want to have fast signaling, right? The faster you're signaling, the faster you can think, for instance. And there's actually a difference between species, I think, in this respect. So now there are two strategies that evolution came up with to increase the speed. One is creating a larger diameter of the axon, and thereby decreasing the internal resistance to passive flow current. So that means that you have the larger your diameter is, the diffusion is easier of these ions. So that will mean that your propagation of the exponential can be faster because you have a faster depolarization of the neighboring compartments. But you know, making larger diameters can work for some animals. That's why it worked for the squid. And this is one giant axon that you have on here. There's enough space, but in your brain, typically in the mammal brain, you want to squeeze as much as neurons as you can in a small volume, right? More neurons is more intelligence, we think. So nature had to come up with a different solution. And that was by isolation of the axons. So by isolation, you prevent actually leakage of current through the membrane. And all the current maintains within the axon, and therefore you have much more diffusion in this direction. And now the trick that nature came up with is to isolate the axon with these myelin sheets. But of course, if you isolate, you also don't have you cannot have sodium channels being present here because they're isolated, right? So there will be no current flow. That's the whole idea of isolation of this axon. So therefore, they had to make these nodes here, so where the sheets were, let's say, missing or uncovered, where there was still access to the extracellular solution for sodium channels to conduct their sodium currents. So you have a high concentration of ion channels in these nodes of Ranvier. Of course, called after the inventor or the discoverer of these nodes. And so it's not like it was depicted here that there's kind of continuous expression of these sodium channels along the axon, but it's really concentrated in these nodes of Ranvier, and that there's just maybe go a little bit quick. That there's just enough. Here you have the nodes of Ranvier. That's why it's actually 3 slides. I forgot about this one. Yeah, so here you have this is staining for the sodium channels. You see they have a high concentration of sodium channels in these nodes and no sodium channels here. And then the length of this myelin sheets is just enough that you have the passive diffusion is still strong enough. Of course, at some point it dies out. So by the time it starts to die out, then you need to have a new, let's say, influx of sodium needed to propagate to the next segment. And that's how this is organized now. Okay? And this drastically speeds up exponential propagation and signaling in the brain. And now really my last slide is what happens if you have a disease, for instance, where your immune system starts to attack these myelin sheets and starts to degrade these myelin sheets. So of course it's obvious that then you lose the exponential conduction speed. That can cause a lot of problems, and that is the disease I think all of you are familiar with. This is multiple sclerosis, MS, and that reduces the exponential conduction speed, and that can lead to muscle weakness, double vision, or blindness in one eye. So you can imagine if your signaling from your eye to your brain is not at the same speed, that you can have all kinds of not coordinated information. So you have also trouble with sensation and coordination, and it can even lead to mental and psychiatric problems. And here is an image of an affected brain tissue of an MS patient, where in red you have the myelin sheets and in green the axons. And you see that there's large parts that can be stained with green. That means that they're not covered by the myelin sheets. And that leads to big parts. Is it shown here? Yeah, not really, but that can lead to this that there's a problem of connectivity here. Very severe disease. Okay. That is just pointing to this point that I was. This is the segment indeed. Okay. Yeah. Again, a animation, and I think that brings me to the last slide. Are there any final questions on this part or the previous parts? If not, then thank you for your attention. Good luck with the exam and the practicals. And